we have f of x equal to x plus 2 over 2. And g of x equal to 3x minus 4. I will also say before we get going, there is the actual practice exam from, I think, 2018. It is very similar in context, in content and length to the actual exam. So if you're looking to practice before you actually take the exam, I would highly recommend going through the practice exam that's posted. I think that would be benefit. And then there are solutions posted as well, so you can check your answers. Okay, no, that's not the right link. There we go. So, yeah. So a couple things we're trying to find here. So first of all, we want to find f of g of 4. Whenever we're finding composition, we want to work from the inside out. So I'm first going to find, just on its own, what's g of 4? Well, g of 4 is going to be 3 times 4 minus 4. That's 12 minus 4, which is 8. So then f of g of 4 is f of g of 4, which is f of 8. And then f of 8, I'm going to plug in there, and I'm going to get 8 plus 2 over 2, which is 10 over 2, which is 5. So there's f of g of 4. Let's now find g of f of 4. So g of f of 4. So now we first have to find f of 4. So f of 4 is going to be 4 plus 2 over 2, which is 6 over 2, which is 3. G of f of 4 is going to be g of what f of 4 is equal to, which is g of 3. So then I'm going to plug in 3 there and get 3 times 3 minus 4, which is 9 minus 4, which is 5. And I will point out, this is a bad example for one reason. Or these two numbers are bad examples because usually, I mirror image my video so I can show you guys my eyebrows, and then I forgot to mirror image it back, so everything looks super backwards to me. Let me check that real quick. I can't operate with backwards writing on my screen. It looks terrible. Okay, so this is a not great example because usually f of g of 4 and g of f of 4 are not equal to each other unless the functions are inverse functions. And these are not inverse functions. So yeah. Yeah, okay. But don't sweat it. It's not that big a deal, right? So you know how to calculate things. Let's find f of 4. So f of 4 is going to be f of, let's see. F of 4 is going to be, let's see, f of 4. Let's find f of 4. So f of 4, I think we already did, right? F of 4 was 3. So f of 4 is f of 3, which is going to be 3 plus 2 over 2. Which is 5 over 2, which is 5 over, I believe it is 5 over 2. You can write it as 2.5. How did we get 4? Well, we were given 4, right? The problem started with find f of g of 4, or g of f of 4, or f of 4, right? That was the initial problem. That's where the 4 came from. But I could have easily said, right, find like f of g of 6. And then, right, it just depends on what you're given. So here, f of g of 6 would be f of, let's see, g of 6 is 3 times 6 minus 4, which is 18 minus 4, which is 14. And then f of 14 would be 14 plus 2 over 2, which is 16 over 2, which is 8. Yeah. Yeah, okay. So that's what's happening here. And the last question that we're asked to find is to find f of g of x. So to find f of g of x, it's equal to f of whatever g of x was. And g of x was 3x minus 4. And then f of that, so I'll remind you guys, f of x is x plus 2 over 2. So f of some stuff is that stuff plus 2 over 2. And then we could simplify. And this is going to be 3x minus 4 plus 2 is minus 2 all over 2. which I would probably leave like that. But if you wanted to, you could write as 3 divided by 2 times x minus 2 divided by 2 is 1. But that would also be fine. You don't have to. Yeah. Okay, so composing functions, something we need to be able to do. Let's look at not problem 4, because that's more graphing, although we will come back to it. Let's look at problem 5, finding the domain of the following functions. So let's look at f of x equal to the square root x to the 6th minus 7x to the 5th plus 10x to the 4th. So when we're trying to find the domain of something like this, we have to say that the insides have to be greater than or equal to 0. So our inequality is that x to the 6th minus 7x to the 5th plus 10x to the 4th has to be greater than or equal to 0. And the way we solve something like this is by factoring. So I'm going to factor out an x to the 4th, with x squared minus 7x plus 10, still greater than or equal to 0. And then if I can factor it more, I do. And I can. X squared minus 7x plus 10 factors as x minus 2 times x minus 5. So x to the 4th times x minus 2 times x minus 5 is greater than or equal to 0. And then we're going to use the number line to see where this quantity is positive and where this quantity is negative. So the things that go on the number line are the values of x that make this equal to 0. So x equal to 0, x equal to 2. In fact, I should give myself a little bit more room. So where is this equal to 0? When x is 0, or when x minus 2 is 0, which means x equals 2, or when x minus 5 equals 0, which means x equals 5. So those are the values that are going to go on the number line, the numbers that make the whole expression equal to 0. So I've got 0, 2, and 5. So if there are 3 numbers, there are 1, 2, 3, 4 separate regions I have to be concerned about. However many numbers are on your number line, the number of intervals we have to look at is 1 more than that, because right, 1 number is going to break up the number line into 2 intervals. 2 numbers breaks it up into 3 intervals, and so on and so on and so on. Every time you add a new number, it's going to give you 1 more interval. So pick a number larger than 5, like 10. Plug it into the factored form. If I plug in 10, I don't care what the number is, I just care if it's positive or negative. 10 to the 4th, positive. 10 minus 2, positive. 10 minus 5, positive. A positive times a positive times a positive, positive. Pick a number between 5 and 2. 3. 3 to the 4th, positive. 3 minus 2, positive. 3 minus 5, negative. A positive times a negative is negative. Between 0 and 2, 1 is a good candidate. 1 to the 4th is positive. 1 minus 2 is negative. 1 minus 5 is negative. A positive times a negative is positive. And finally, pick a number negative, like negative 2. Negative 2 to the 4th is positive, right? The negative number to an even power is positive. Negative 2 minus 2 is negative. Negative 2 minus 5 is negative. So a positive times a negative is positive. Before we get going here, I'm going to do 2 things. I'm going to circle the parts I want. I know I want it to be greater than or equal to 0. Greater than 0 means I want it to be positive. So I want the positive parts. I also want the parts where it's equal to 0, meaning I want 0 and 2 and 5, because those numbers make the whole thing equal to 0. And it's okay to take the square root of 0. So the domain here would be all of this, and all of this. So the most correct way to write this is the interval from negative infinity to 2 with a bracket. And we don't have to stop at 0 because we have everything to the left of 0, everything to the right of 0, and 0 itself. So it's just kind of the whole thing from negative infinity to 2. Union bracket 5 to infinity. Just to kind of show you how this would be slightly different if instead the function was g of x equal to the log base 3 of the same expression. So if we have the same expression, except it was log base 3 or log base anything, the difference between a log and a square root when you're talking about domain is that for a square root, you can take the square root of 0. So it's okay to say that the inside stuff is greater than or equal to 0. For a logarithm, you have to have it just be greater than, but not equal to 0, because you can't take a logarithm of 0. So here, we want the positive part still, but we would not want any of these endpoints, any of these zeros of the function. So if it was the logarithmic one instead, the domain would be everything from negative infinity to 0, but we don't want 0. So we use a parentheses. Union 0 to 2, but we don't want either of the endpoints, so we use parentheses. Union, we don't want anything between 2 and 5, because it's negative there. We do want everything after 5, so 5 to infinity. So that's kind of the difference between including all the zeros of the function and excluding all the zeros of the function.
Can I ask you a quick clarifying question? So did you figure out, did you assign positive and negative values by plugging in our x values into the equation? So for example, to check 0, you put in 0 for x and solve?
I did not. So I'm not actually plugging in these values here, because these are the values I got by saying what makes this equal to 0.
Oh, right.
If I plugged in 2, I'd get 2 to the 4th times 0 times 2 minus 5. But anything times 0 is 0.
Oh, right.
So what I'm doing is I'm actually picking a point in between each of those zeros. So I'm picking a point in each interval. So let me draw here. So right, so in this rightmost interval, I picked x equal to 10. But you can pick anything bigger than 5, like 6 or 1,000,000. And in this interval here, I picked x equal to 3. And in this interval here, I picked x equal to 1. And in this interval here, I think I picked x equal to -2. So you're never picking these numbers, because these numbers will always make it just equal to 0. You're picking the numbers that make it, that are actually in between those numbers. And then asking yourself, if I plug that number in, is this expression positive or is it negative?
Right.
Actually, sorry, except I was using this expression because that's easier. You want to use the fully factored expression if you can.
Thank you.
You're welcome. Good. It's a good question. Right. The other one here is, I'm going to change it a little bit. I'm going to change the second one. So let's say we had, sure, f of x equal to the log base, just log of 4 minus x squared. I'm going to say divided by x minus 1. So there are two things we have to deal with here. Okay, turn it back, sure. Sure thing. Give it a minute, take some water. Guys, like, I spent lots of time practicing that eyebrow thing. Now I was gonna do it all the time. I mean, yeah, it's been true for 30 years, so yes. So for the domain here, there's two things we have to worry about. We have to worry about division by 0. So we know we want to exclude x minus 1 equal to 0, aka exclude x equal to 1. So we don't want 1. 1 is out. So if you want, so at this point you could on your number line be like, okay, there's 1, I don't want it. Everything else so far is good, right? Like if the function was just 1 over x minus 1 or 2 over x minus 1 or whatever over x minus 1, that wasn't a problem on top, then you could say, okay, my domain is everything from negative infinity to 1 and 1 to infinity, right? When you're talking about a denominator, don't give the denominator to be negative or positive, it just can't be 0. But then we have a problem on the top. For the top, we also have to worry about the inside of the logarithm. So it's not that specifically it's in the numerator, right? It could just as easily be somewhere like, I could have said the function was 1 over x minus 1 plus log base, whatever, it's not log base 10 of 4 minus x squared. And this would have the same problems. I still can't have x equal to 1, and I still have to have the insides of the logarithm being non-negative, being positive and not 0. So being positive, right? Sorry. I'm trying to say it's not so much that we care about what's happening in the numerator, it's that we care that there is a logarithm. So the insides of the logarithm, 4 minus x squared, have to be positive. And I really recommend factoring. You could bring x squared over and then square both sides, but you're going to probably miss the -2. I really think it's going to be better to just factor this as 2 minus x times 2 plus x greater than 0. And then we know that x equal to 2 makes this equal to 0, and x equal to -2 makes this equal to 0. So I'm trying to figure out what's going on with this inequality. So I feel like it's actually, I know I said you could put this on here, I feel like it's actually a little premature. You probably want to deal with the inequality on the number line first, and then after that, think about the things you want to exclude. So I'm going to go back and actually not put the 1 there just yet. I know it's going to get excluded, but that's kind of like the last thing I need to do. So I need a 2 and a -2. So I'm going to pick something bigger than 2, like 3. And check out my inequality. If I plug in 3, 2 minus 3 is negative, 2 plus 3 is positive, a negative times a positive is negative. So when I pick a number over here, it's negative. And I could have picked anything. I could have picked 3, I could have picked 3 billion. 2 minus 3 billion is negative, 2 plus 3 billion is positive. A negative times a positive is negative. Right? Basically, once you found the things that make it 0, if you're fully on this side of 2, well, it can't ever equal 0 over here. So it's either always positive or always negative. And then we pick something between -2 and 2. I would pick 0. If plug in 0, 2 minus 0 is 2, which is positive. 2 plus 0 is also positive. Positive times positive is positive. So right there I picked x equal to 0. And finally over here, I'm going to pick something like x equal to -5. Or -3 if you want to be boring. 2 minus -5 is positive. 2 plus -5 is negative. A positive times a negative is negative. So then we want the positive parts. We want it to be greater than 0. For these domain questions, you're always picking the positive parts. Correct? It's the square, well, I should say, for a square root, it's the positive parts and the endpoints. For a logarithm, it's the positive parts and not the endpoints. And then for division by 0, you're just pulling points out. That's actually positive or negative. So I want that, everything between -2 and 2. I don't want the endpoints. And then I also have to remember, oh wait, I also don't want 1, right? So there's 1 right there. I don't want u either. The reason I didn't want to include 1 on my number line before this is because I don't want it to be a place where I'm also like checking in between 1 and 2 and -2 and 1. I don't need that. So I want everything between -2 and 2, but I don't want 1. So my domain here is -2 exclusive up to, I was going to go to 2, but I have to stop at 1 and exclude it. Union back starting at 1 up to 2. So there's my domain for this problem. Everything from -2 to 1, union 1 to +2. All right. Erase the other side. You guys a chance to look at that while I erase. All right, week 8. We have 2 more weeks left, and then finals. I forget what day our finals on, but I'll try to make our final available relatively early. I know I should. Let me not talk about finals when you have a midterm. So we'll talk about finals next week. But they are coming up, so you should be aware of them. Find the inverse for each of the following functions. So let's see. Our first function, f of x, is 7x minus 2 over 9. I want to find the inverse. So the process is always the same kind of stuff. The first thing we're going to do is we're going to write y equals 7x minus 2 over 9. The second thing we're going to do is we're going to switch all the x's and y's. So that means every x has to become y, and the one y, right, you should only have one y, should become an x. So there's multiple x's over here. Each of them has to become y. Keep grabbing like this, throw on my shirt. Don't keep losing my pants. Okay. sorry, so step 2, y becomes x. Every x, which is only one of here, becomes y. So then we have to solve for y. So multiply both sides by 9. 9x equals 7y minus 2. Add 2. So 9x plus 2 equals 7y. Divide by 7. So y equals 9x plus 2 divided by 7. You can probably stop there, but if you want to be super precise, the last step is to then write that f inverse of x is equal to 9x plus 2 over 7. Okay, that's the process. Let's do another one. The next one is, the function is f of x equal to log base 2 of x plus 1 minus 3. So first things first, we're going to write it as y equal to log base 2 of x plus 1 minus 3. And then we're going to interchange x and y. So we have x equal to log base 2 of y plus 1 minus 3. To be able to isolate y, you have to first be able to isolate the logarithm. Meaning, so I've got log base 2 of y plus 1 and then minus 3. I need to get rid of that minus 3. I need to add 3 to both sides. So I can say that x plus 3 equals log base 2 of y plus 1. And then I'm going to rewrite it. My base is 2, my power is x plus 3, and it's equal to y plus 1. So 2, that's not my best 2 ever. 2 to the x plus 3 equals y plus 1. And then solving for y equals 2 to the power of x plus 3, and then minus 1. And then you could write your final answer as f inverse of x equals 2 to the x plus 3. That's how you do this problem. Got one more. The last one here, f of x equal to 1 over x to the 5th plus 4. So first, we're going to write it as y equals 1 over x to the 5th plus 4. Interchange x and y. So x equals 1 over y to the 5th plus 4. And then the hard part, the solving. So I would first subtract 4 from both sides. So x minus 4 equals 1 over y to the 5th. And then you can code 2 different ways, which are essentially the same. You could either take the reciprocal of both sides and say 1 over x minus 4 equals y to the 5th. Or you could multiply both sides by y to the 5th. So you could say x minus 4 times y to the 5th equals 1. But then you're going to try and solve for y to the 5th, so you're going to divide by x minus 4. And y to the 5th is going to equal 1 over x minus 4. Either way, you're getting to the same place. Then we're going to solve for y by taking the 5th root of both sides. So y is equal to the 5th root of 1 over x minus 4. All right. Yeah. Let's look at the next one. All right, my face is in the way there. We'll try and get this video of this posted up relatively quickly so that if you want to go back and look at it again, you certainly can. So let's see, determine if the following function is even, odd, or neither. Okay, just a reminder, even functions, f of negative x equals f of x. Odd functions, f of negative x equals negative f of x. So we're always starting with f of negative x. So here's the first one. the function is 3x to the fourth minus 2x squared. So let's look at f of negative x. It's 3 times negative x to the fourth minus 2 times negative x squared. And if we simplify this, we're going to get, so again, when you raise a negative thing to an even power, you always get that thing becoming positive. So I'm going to get 3 times positive x to the fourth minus 2 times positive x squared. That's the same, which means it's even. Okay, check the next one. What have I got? X cubed over x to the 6 plus x squared plus 1. X to the 6 plus x squared plus 1. Okay, so again, I'm going to start the same thing. I'm going to look at what is f of negative x. Well, it's negative x quantity cubed over negative x quantity to the 6th plus negative x quantity squared plus 1. Right, you're just plugging in negative x wherever there was an x. And then we're going to simplify this. So a negative x to the odd power is going to stay negative. So negative x cubed is negative x cubed, right? But it's not this anymore. It's right. I'm trying to pause there so you can hear it, right? It's not negative x quantity cubed. It is negative x cubed over positive x to the 6th plus positive x squared plus 1. That's not what we started with, but it definitely is the same as negative f of x, right? Because negative f of x is negative x cubed over x to the 6th plus x squared plus 1. And if you're multiplying a fraction by a negative 1, right, because that's really a negative 1 if you want it to be, when you multiply a fraction by negative 1, you multiply either the top or the bottom by negative 1, but not both. Because you multiply both, you're really multiplying by negative 1 over negative 1, which is positive. So if I multiply the top by negative 1, I do indeed get this. So it's odd.
Could you explain that one more time?
Sure. The part about multiplying by negative 1?
Yeah.
Okay. So let me go up here. So if you multiply negative 1 times this fraction, you can either think of it as negative 1 is negative 1 over 1 times the fraction x cubed over x to the 6th plus x squared plus 1. And when you multiply fractions by fractions, you multiply the tops together and the bottoms together. So this is going to be negative 1 times x cubed over positive 1 times x to the 6th plus x squared plus 1. What I want to point out is negative 1 times a fraction is not equal to negative 1 over negative 1 times the fraction. Right, so I really, really want to stress when you multiply a fraction by negative 1, you do not multiply both the top and the bottom by negative 1, because you're not really multiplying by negative 1. Right? Negative 1 divided by negative 1, that's equal to positive 1, not negative 1. Does that clarify what I'm saying for you?
Well, doesn't that make the top negative though? And then.
Yeah, that's what I'm saying. That makes the top negative, which makes negative f of x equal to f of negative x.
But I thought it had to match the original function.
That's if we're trying to show it's even.
Oh, so to show if it's odd, it has to be the opposite of the original function?
So to show it's even, right, even is f of negative x equals f of x. Right, it's the same as we started with. To show it's odd, f of negative x has to equal negative f of x.
Okay, thank you.
And then if it's neither one of these, the function's neither even or odd. like in the last example here. So
Gotcha.
in this last one, f of x equal to, here you go, x to the fifth plus x squared. First, f of negative x, we get negative x quantity to the fifth plus negative x quantity squared. Negative to an odd power stays negative. Negative to an even power becomes positive. This is clearly not what we started with. So it's not even. But then if we look at the negative of what we started with, negative f of x is negative the whole thing. -1 times the whole thing, you distribute in this case, and you get negative x to the fifth minus x squared. So we also see that negative f of x does not equal f of negative x, right? This and this also not the same. So f of negative x isn't equal to f of x, so it's not even. And negative f of x also isn't equal to f of negative x, so it's not odd. So this function is neither odd nor even. Okay. Good with that? Yes. Okay. Part 8. Question 8 on it. Using functions inverses to find domain, find range. Yeah. So I definitely saw a few of you on the homework. You very, very capably found the inverse of a function, and then you found the range of the inverse, but you actually wanted to find the domain of the inverse to find the range of the original function. So let's look at this original function. F of x equal to 2x minus 3 over 4x. And we're being asked to find the range, but let's go ahead and just mention what the domain is here. So I know that for sure the domain x can't be 0. But everything else is valid. Now, really, actually, if I was actually finding the domain, that's the question, I would write it using the interval notation. And you should write your domain and range answers using the interval notation. But I want to find the range. So to find the range of f of x, I am going to find the domain of the inverse function. Meaning I have to find the inverse function. So I'm going to find the inverse. So I'm going to start with y equal to 2x minus 3 over 4x. I'm going to change all the y, the only y to x, and all the x's to y's. I'm going to multiply both sides by the denominator. So I'm going to get x times 4y equals 2y minus 3. And then I'm going to bring all the y's to the same side. So I guess since I've already got y's on the left and no non-y's on the left. 1 second for Daniel. Let me finish this problem, then we can go back to the previous one. So I'm going to bring all my y terms to the left. So I'm going to have 4xy is how I should write that. Minus 2y equals -3. Factor out a y because we're trying to solve for y. Look at y times 4x minus 2 equal to -3. And then finally, y equals -3 divided by 4x minus 2. So the domain of this inverse, so I should say the inverse function is -3 over 4x minus 2. And the domain of this inverse function is, well, x can't be, let's see, I can't have 4x minus 2 equal to 0. So solving that, you get 4x equal to 2, and get x equal to 2/4, which reduces to 1/2. So the domain of the inverse function is everything except for 1/2. So the range of the original function is everything except for 1/2. It's -infinity to 1/2 union 1/2 to infinity. So Again, I'm not trying to find the range of this. I already know the range of this isn't 0. It's the same as the domain of this. I'm trying to find the domain of this inverse function to find the range of the original function. All right, Fernanda, you had a question about the previous example. Shoot, go ahead. Right here? No, it would not. Because it's not, so negative x squared is not the same as negative x quantity squared. This negative x squared, if you read it this way, means we're doing the squaring first and the negative after that. So this is really negative x squared. Hopefully that clarifies things. So basically a negative thing being squared, it's only being, the negative part's only being squared if it's inside the parentheses. Okay, let's go back and look at problem 4. So it's a graphing problem, they're piecewise functions. So I'm going to graph f of x equal to e to the x when x is less than 0, less than or equal to 0. And x minus 2 in absolute value when x is greater than 0. So we know what each of these looks like. We know that e to the x looks like this. Has a y-intercept at 0, 1. And we know that the absolute value of x minus 2 looks like your usual absolute value function shifted 2 to the right. Has an x-intercept at 2, 0, and a y-intercept at 0, 2. So now I want pieces of each of these. Now, be careful. This is e to the x when x is less than or equal to 0. That means I want x to be to the left, right? That's where x is less than or equal to 0. So I want this part of the graph. I do not want this part. For x minus 2 in absolute value, I want where x is greater than 0, which means I want everything to the right, which means I want everything starting here. So I want all of this. I do not want this. Okay. So there's the point 0, 1, there's point 0, 2. I want my e to the x graph. And then I want this graph. It's got an x-intercept of 2, 0. It's only got one y-intercept though. So one of these points should be filled in and one of these points should not be filled in. And the one that should be filled in is the one that goes with the one that says x equal to 0. So x less than or equal to 0, which has the x equal to 0 part, goes with the e to the x graph. So the e to the x graph is the one that should be filled in there. And then the other one should not be filled in. So that's the point 0, 2. I still want to label that point because even though it's not actually a point on my graph, it's a hole that is important. And then that point there is 0, 1, which, yeah, okay. I ran out of the room, sorry. So there's my piecewise graph. Let's look at the other one. And then we'll do a rational function and a polynomial. Yeah, we can get 2 more graphs in. 3 more graphs in. Again, there are solutions to all of these posted on Canvas. So if we didn't get something that you really want to see, you can always check out Canvas. Well, let's look at the other piecewise function. f of x equal to x squared when x is less than or equal to 0. Natural log of x when x is greater than 0, but less than or equal to 1. And I'm going to change this last part actually, and let's make it, yeah, that's not very exciting. Let's make it 4 minus x when x is greater than 1. Okay, and I'm just going to try and do this all at once. So I know that 0, 1 are important places because that's where things are changing. So we know what x squared looks like. It's your usual parabola. And it does this. And it is defined as 0. So I plug in 0, that's what I get. Okay, and then to the right of 0, I have the natural log function. We know the natural log function looks like this. You've got a vertical asymptote and it has the intercept of 1, 0. So I'm going from 0 to 1. So I really just want this section right here. So I'm going vertical asymptote up to this point here. And it is filled in because, again, it's less than or equal to 1. And then finally, I have the graph y equal to 4 minus x. I know that y equal to 4 minus x is a straight line. It has a downward -1 slope. And when I plug in 1 for x, if I could plug in 1 for x, 4 minus 1 would get me 3. So if I could plug in 1, I would get 3, but I can't, so it's a circle there. It's an open, sorry, it's a hole, not a circle. And then it's going to go down to the right. This does have an x-intercept when x is equal to 4. Right? If we set 4 minus x equal to 0, we get 4 equal to x. That's how it looks. And we should have little arrows, right, to indicate it keeps going that way, it keeps going that way. So that's how that piecewise function looks. And I would label this point or make sure it's very clear that whoever was reading it knew that that was the point 1, 3. That's the point 1, 0. You shouldn't have to label the origin, right? If your point is hitting the origin, we all know it's the origin. Ah, pen on my finger. Gross. Okay. So I'm going to try and throw 2 more graphing problems at you real quick. One of them is pretty straightforward. The other one's a rational one, so I might go over by a minute or 2. Sorry. If you don't want to stick around, you obviously don't have to. I mean, you don't have to be here at all, really. Attendance, I do take attendance, but it's not part of your grade. So if you never wanted to come, you don't have to. But I mean, I hope you feel like you're getting value out of seeing things done. So I want to graph this. I'm going to talk about the end behavior. So the end behavior, we know that the degree is 6. Right? It's 4 plus 1 plus 1. I should say really 4 plus 1 plus 1. And the leading coefficient, if you multiply it out, you'd have an x to the 6 with a positive leading coefficient. So we know that these two things together, it being even and having a positive leading coefficient, means it's up on both sides. Y-intercept, also not too terrible. Set x equal to 0, f of 0 is 0 times it doesn't matter. 0 times anything is 0. X-intercepts, we set the whole thing equal to 0. X to the 4th times x minus 2 times x minus 5, 0. From this one, we get x equal to 0 with a multiplicity of 4, meaning we're going to bounce. From this factor, we get x equal to 2 with an odd multiplicity, meaning we're going to cross. And the same deal here. From this one, we get x equal to 5, also with odd multiplicity, meaning we're going to cross. So our graph has intercepts at 0, 2, and 5. Up on the left, up on the right. So we're up, come down, we bounce at 0, we go through at 2, we curve through at 5. That's what it looks like. Okay, one more graph for you. The rational function, meaning it'll probably have horizontal and vertical asymptotes. So let's take a look here. It's, okay, sure. It's x squared minus, it's y equal to x squared minus 4x plus 4. Yeah, it's got to be plus 4. Over x squared minus, really, who picked that? Minus 2x plus 1. Okay, so if you're going to graph this, something you want to do is factor. So the top factors is x minus 2 times x minus 2, which is x minus 2 squared. And the bottom factors is x minus 1 times x minus 1, which is x minus 1 squared. Y-intercept, I plug in x equal to 0, I get 0 minus 0 plus 4 over 0 minus 0 plus 1. So I get y equal to 4 over 1, which is 4. X-intercept, set the top equal to 0. X minus 2 squared equal to 0 gives me x equal to 2 with a multiplicity of 2, meaning it's going to bounce. Vertical asymptotes, set the denominator equal to 0. You're going to get x minus 1 squared equal to 0, which is going to give you x equal to 1, also with a multiplicity of 2. Meaning at your vertical asymptote, both sides are going to go up, or both sides are going to go down. And then finally, the horizontal asymptote. The degree on top is 2, and it's equal to the degree on the bottom. Which means we do have a horizontal asymptote. The horizontal asymptote is y equal to the leading coefficient on the top divided by the leading coefficient on the bottom. So 1 over 1. Not 2 over 2, 1 over 1. I know those equal the same thing, but there's a difference in how you think about it. Okay, so let's graph it. 1, 2, 3, 1, 2, 1. Okay, so let's see here. Y-intercept is 4. X-intercept is 2. Vertical asymptote is positive 1. Do draw your asymptotes in. Horizontal asymptote is positive 1. We're going to start here, and as we go to the right, we have to go up to infinity because we can't go down and cross the x-axis where there isn't an x-intercept. On the other side, we also are up because our vertical asymptote was up on both sides. We're going to come down. We have to hit that intercept and bounce off. So we're going to come down. We're going to cross the horizontal asymptote and bounce off, and then get closer and closer to the horizontal asymptote. To the left, the only thing we have to do is get closer and closer to the horizontal asymptote. So that's what that graph looks like.